All right, so today what our goal is to prove that not ATM is not inside of sigma 1. Now, let's just recall that ATM is inside of sigma 1, and some string x is inside of ATM if and only if x equals the encoding of m and w, where m is a Turing machine and w is inside of the language of m. Okay, so what the heck is not ATM? So not ATM is the negation of this. So that means that x is inside of not ATM if and only if x doesn't equal mw, meaning that it's some sort of invalid encoding, or it does equal mw, but w is not inside of the language of m, meaning that m does not accept w, meaning that m says no or loops. Okay? So basically what not ATM does, I mean, there's a trivial thing that it does, which is it checks to make sure the encoding is valid. Okay, so that's boring. Okay? The next thing that it does is it checks to make sure that it doesn't accept. Also boring. The more interesting thing that it does is it checks to see if m loops. So what not ATM does is it figures out if m on w loops. That's what m does. That's what not ATM does. It can figure out if when you run w on m is going to loop and diverge. I.e., what it does is it predicts if m halts. And so therefore, we call this the halting problem. So the halting problem is the problem of figuring out if when you run a program, that program on given input will eventually fail or not. Okay, now what we are going to do is prove that that is not inside of sigma 1, meaning that you cannot write a program that will do it. And it's actually kind of trivial to do this. And here's the way that we do it. The first thing is that we're going to prove a little helper theorem. And this little helper theorem is that A is inside, actually, let's not use A because we're talking about ATM. Let's use a different symbol. We'll say that some language X is inside of sigma 0 if and only if X is inside of sigma 1 and not X is inside of sigma 1. Okay, so let's do the proof of this. So remember, an if and only if, right, is a bi-directional proof. Okay, so that means that we need to prove two things. We need to first show that if we know that X is inside of sigma 0, then that implies X is inside of sigma 1 and not X is inside of sigma 1. So how can we do that? Well, that means that we have some machine, let's call it M, and we want to produce a machine F and G. Well, F is just equal to G, right? Sorry, F is just equal to M. Because the way that something is inside of sigma 1, X being inside of sigma 1, we could just run sigma 0. Because remember, sigma 1 doesn't say it must loop sometimes, it just says it's allowed to loop. Okay, so that means that F is just equal to M. And G of course, if we run G of X, then what we just do is we just return the negation of calling M on X. So we just run this machine, it returns yes or no, and we just return the opposite, okay? And then that is definitely inside of sigma 1. Also, it's kind of obvious, right, because we know that we we know that this machine won't loop, so this also doesn't loop, okay? So this, by the way, kind of shows that sigma 0 is closed under complement. Under complement. All right, but now let's do the other direction. So the other direction says, if X is inside of sigma 1, and not x is inside of sigma 1, then that implies that x must be inside of sigma 0. So that means that we have f, and we have g, and we want to get m. So how can we do that? Well, here's what we do. We say that m of x, okay, is equal to, we non-deterministically run f on x and g on x. And if f of x says yes, then we say yes. So yes goes to yes. And if g says yes, then we return no. And the reason we return no is that f, it identifies when it says yes, and g identifies when it says no. And so therefore we say no. Now the thing is that if x is not inside of f, then that means that it could loop and run forever. So that means that we can't really trust when this says, well, when it says no, we can definitely say no. But we can't do anything based on the looping because we can't observe looping. In contrast, when g is done, that means that we definitely know it is rejected, so we can stop. And the thing is that since both of these are inside of sigma 1, one of them is eventually going to return. They can loop, like this one can loop when this one says yes, and this one can loop when that one says yes. But if this one loops, that one had better say yes. And if this one loops, that one had better say yes. So all we need to do is just run them both in parallel, i.e. non-deterministically choose between them, and then, return yes to whichever one comes back. Okay, so it's very trivial to do that. We, in fact, don't even need full non-determinism. We just need to do a parallel run of them. Okay, so it's trivial to do this. So now we know that if both things are in sigma 1, then that means that the thing is inside of sigma 0. All right, so now what does this mean? Okay, so this is actually a big deal. So we know that it is equivalent to say x is inside of sigma 0 as it is to say x is inside of sigma 1 and not x is inside of sigma 1. Those two things are equivalent things to say. Well, we already know that ATM is not inside of sigma 0. We already know that. Well, what does it mean to say that something is not? Well, in general, anytime you write not P, what you really mean is that P implies false. Okay? So this thing right here is equivalent to saying ATM inside of sigma 0 implies false. Okay? Well, we know that ATM inside of sigma 0 is the same as that. So that means that ATM inside of sigma 1 and not ATM inside of sigma 1, that implies false, which means that this is equivalent to saying that it is not the case that ATM is inside of sigma 1 and not ATM is inside of sigma 1. Well, anytime we have a not like that, we know that not of P and Q is the same as saying not P or not Q. So that means that this is the same as saying that ATM is not inside of sigma 1 or not ATM is not inside of sigma 1. Well, we actually know that ATM is inside of sigma 1. We've already proved that. We have an implementation. You can go look at a universal Turing machine. So that means that this right here, we know that that right here this is equivalent to false or not ATM is not inside of sigma 1. Well, anytime that you have false or P, that is equivalent to just P. So therefore, this is equivalent to not ATM is not inside of sigma 1. And boom, we just did it. So we just proved that because we know that ATM is not inside of sigma 0, and we know that whenever something inside of sigma 0, it must be inside of sigma 1 and its complement is inside of sigma 1, therefore we can conclude that not ATM is not inside of sigma 1. And that's it. Okay? So we just proved that the picture looks like this. We've got all, which is the power set of sigma star. We have fin, which is 0, 1. We have reg, which is 0 star, 1 star. I'm sure that you're getting bored of seeing this. We have CFL, which is 0 to the n, 1 to the n. We have sigma 0, which is 0 to the n, 1 to the n, 0 to the n, and a DFA. We have sigma 1, and sigma 1 has ATM. And then outside of here, we have the complement of ATM. So this picture is what we've proven this whole time. We've shown that there are some finite languages, okay? And then we do some finite sets. And then we have a model for describing sets that are infinite, but that are understandable by programs in our universe. We have schematics for those that use sets. We have schematic for those that use memory. We then talked about how understanding Turing machines, analyzing them, and simulating them, there's no shortcut. So there's no way to turn something that might loop into something that won't loop. And we can't even look at something and tell whether or not it's going to loop. It's actually it's not just that when we try to do that we'll loop, it's that when we can't even try to do that, there's no way to write a program that will always return a true answer with this. And so it's not like it could return a true answer, but you couldn't trust it because it wouldn't be a valid program. So that's the picture that we have right now. Now, what would be really nice is next to prove that there's not just one program that is inside of all but not inside there, but actually that there's more programs than that. Remember that every time we've done this in the past, when we showed that something was outside of reg, we showed that there's in fact an infinite number of things outside of reg. And when we showed that things were outside of CFL, we showed that there were an infinite number of them. It would be really great to show that there's an infinite gap between these things. And we can do that, but we have to do it in kind of a weird way. So here's the weird way that we need to do. So what we need to do is we need to talk about what the different sizes of infinity are. What are the sizes of infinity? And here's where we're going to go with this. We know that all is infinitely large. And we also know that sigma 1 is infinitely large. But we're going to show that sigma 1 is a smaller kind of infinity than all. That's what we're going to say. So let's look at kind of an example. Like the most prototypical infinite set are the natural numbers, which we write as n. So that's 0, 1, 2, 3, 4, etc. We also have stuff like z, which are the negative numbers. So we got 0, minus 1, 1, minus 2, 2, minus 3, 3. We've got q, which is all the rational numbers. So that's stuff like 0, 1 divided by 2, 3 divided by 4, negative 4 divided by 6, etc. Okay, so there's lots of those. And then we also have the real numbers. And so the real numbers, they have stuff like 0, 1, 2, okay? They've got stuff like 3/4. But they also have stuff like pi and e and the square root of 2 and, 3 repeating and stuff like that. So they've got all sorts of exotic numbers. So each one of these is a different infinite set. And what we would like to do is compare infinite sets. Now, think about how you would compare like a normal set for how big it is. So if I were to show you the set that contained kisses and hugs and puppy dogs, I could ask, how many things are inside of that? And you are going to look at that and you're going to say, boom, there's 3 things. And that's kind of obvious, because we just count them, 1, 2, 3. But if I were to ask you a question like, how many things are inside of 0 star, 1 star, how do you even start talking about that, right? Because you can't count them, and you can't count them because there's an infinite number of them. So we have to change what it means to talk about the size of a set from thinking about it not in terms of a number, but in terms of another set that's the same size. So rather than saying that we have a function that takes a set and returns a number, instead what we want to do is we want to think about there being an operation that compares one set and another set and says that they're the same size. Okay, that's what we want to do. So we want to define what it means for two sets to have the same size. So sets have the same size. Same size if, so imagine we have one set, call it A. We've got another set B over here. Okay, and they've got stuff in them. Okay, so you and I can look at this and we know that they're the same set. But how could we figure out that they're the same set if we can't count them? Well, what we can do is we can write a function, f, that maps elements of f to elements of b. And we know that if f exists, and it has certain constraints, right? What are the constraints? Well, there can't be an extra thing over on the A side that isn't mapped to something on the F side. And there can't be an extra thing over on the B side that isn't mapped to something on the F side. Well, that means that f has to be a function that goes from A to B, and it has to have two properties. The first property is called 1 to 1. And this property goes like this. For all x and y inside of A, f of x equals f of y implies that x equals y. So what does that mean? That means that if we map A to something over here and B to something over there, then those two things, if they happen to be the same thing, must mean that the things over here were the same. 1 to 1 guarantees that there's not something that's extra on the B side. Sorry, guarantees that there's not something that's extra on the A side. Because the thing is that if there was an extra thing over here, then it would have to map to something. And that something would mean that this thing and that thing were equal to something, but they themselves were not equal. So 1 to 1 guarantees that that doesn't happen. Okay? The other property is called on2. And it guarantees that there's no leftover B stuff. And it looks like this. It says, for all z's inside of B, there exists an x inside of A such that f of x equals z. So this basically says that everything that's over here in the B space, there's something over in the A space that maps to it. There's nothing that's left out. So if a function has these two properties, then we know that the two sets are the same size. Right? So we say that same size A and B is defined as there exists a function from A to B where that function is 1 to 1 and the function is on 2. And if the function exists, then that means the two sets are the same size. Okay, so now what we can do is we can prove a theorem like the following. We can prove a theorem that says the natural numbers, those are the numbers 0, 1, 2, 3, 4, etc. They are the same size as the even numbers. The even numbers being 0, 2, 4, 6, 8, and so on. Now, intuitively, this is crazy, right? Because we know that the even numbers are a subset of the natural numbers. In fact, you take all the natural numbers, half of them are even. So how can something that is everything be the same size as something that is just half of that? Well, we know that they're the same size because such a function exists. And here's the function. We can write a function that goes from a natural number to an even number. And here's the function. F of x equals 2x. Now we want to prove that they are one-to-one and onto. So we want to prove the theorem that if 2x equals 2y, then that implies that x equals y. Trivial, right? You just divide by 2. We also want to prove the theorem that for all even numbers, there exists a number, so for all n inside of the evens, there exists an x inside of the naturals where 2x equals n. Well, guess what? What an even number is a number that's 2 times something. So that means that this is really the same thing as saying for all y inside of the naturals, there exists an x inside of the naturals such that 2x equals 2y. Because what a natural number is 2 times something. So of course, what is x? X is exactly y. Okay? So it's actually trivial to prove that the natural numbers are the same as the even numbers. We say that anything that is the same size as the natural numbers is called countable. So if a is the same size as the naturals, then a is countable. And the guy who came up with this theory is called Georg Cantor. And he called the countable numbers Aleph 0. I can't draw an Aleph, I draw it like a chi. Aleph is like the first Hebrew letter. Okay, so it's Aleph 0 are the countable numbers. All right. So what's next? Well, we know that the natural numbers are they're like the countable ones, and they're the same size as the even ones. What we'd like to do now is show that they're the same size as the rational numbers. Actually, let's not do the rational numbers. Let's show that the natural numbers are the same size as the integers. So the integers, they just have a positive and negative number. And here's a way to think about that. The natural numbers are the line. So we have the line, and we tick off all the elements. This is n. Okay? And then z, however, goes in both directions. Okay? Now, to make a function that goes from n to z, you can kind of think of that as you have to give an order for how to explore the z numbers. What that means is that we have to say which one of these z numbers is the first one that you see, and which is the second one that you see, and which is the third one that you see. Well, it's actually really straightforward to do this. We'll say that you'll start at 0, and then from 0 you'll go to 1, and then from 1 you'll go to -1, and then from -1 you'll go to +2, and then from +2 you'll go to -2. Okay? So what we'll do is we'll say that the first number, that is f of 0, is equal to 0. Right? Then we'll say that, then we can say, like, what is the next one? Okay? So we'll say that the successor of 0 is 1. And we'll say that the successor of any positive number n is equal to the negative version of that number n. And then we'll say that the successor of any negative number n is equal to the positive number n plus 1. What I've just done is I've told you what is the first number, what comes after it, and then what comes after that, what comes after that, what comes after that. What I've done is I've now described the order in which you visit all of the numbers. So this now shows that such a function exists because we know that every z will get visited and every n will get mapped to something. So can we do the same thing for the rational numbers? And the rational numbers, by the way, they're just really the same thing as pairs of naturals, right? Because a pair of a natural is like a plane. Like the things in Q are really just elements of the Cartesian plane. Actually, just the one-dimensional Cartesian plane. Not the one-dimensional, the like one quadrant of the Cartesian plane. So we have 0, 0, we have 1, 0, 0, 1, and so on. So this right here is one way to think about what Q is. Okay? And obviously we could, talk about the entire thing. If rather than having Q be NN, if Q were Z, Z, then it would just be the other quadrants too. Okay? So how can we do that? Well, we can follow the same sort of idea. We'll say we'll start here, and then we'll go there, and then we'll go here, and then we'll go there, and then we'll go there, and there, and there, there, and then we'll move over here, and we can keep tracing larger and larger rectangles. And if we do that, we'll eventually visit everything, and and this right here is an order that works. Now, there's another order, though, that is not this box order, that's called the triangle order. And the triangle order works a little bit differently, and there's a function that, that Cantor himself came up with. It's called the Cantor pairing function. And what the Cantor pairing function does is it takes something inside of n cross n and turns it into something inside of n. And it looks like this. So f of xy is equal to 1/2 of x plus y times x plus y plus 1 plus y. And that function is reversible. Now obviously, once we now know that n and n by n is the same size, we also know that they're the same size as n cross n cross n. Because why? Well, we just take our three numbers, x, y, z, and we combine the first two into a new number, u, z, and then we combine those into a new number, v, and then there we go. And we can do this arbitrarily. So in fact, n is the same size as n to the k for all k. And here is where we have our most interesting thing. By the way, if you want to look more about this, I have a research paper that explores ways of combining things like this in ways that are more effective than just doing it in an iterated fashion. So if you search for fair enumeration combinators, with Max New and me, Jay McCarthy, you can read about that. All right. So here's a claim. Sigma 1 is the same size as n. Sigma 1 is countable. Now, why is it countable? Well, we know that sigma 1 must be smaller than the Turing machines. Now, why is that? Well, sigma 1 are all the languages that could be represented by any Turing machine. And we know that I could just take a Turing machine that has 4 states and recognizes some language, and just make another one that has 5 states and recognizes the same sort of thing. Okay, so because of that, that means that there's duplication, right? All right. So sigma 1 is smaller than the Turing machines. And the Turing machines, they must be smaller than n by n. And why must they be smaller than n by n? Well, remember, to encode a Turing machine as a binary number, the first thing that I do is I say how many q there are. Then what I do is I say how many gamma there are. Oh, sorry, n by n by n. They're smaller than n by 3. So I say how many q there are, how many gamma there are, and then what I do is then I just have the encoding of q0, the encoding of delta, the encoding of qa, and the encoding of qr. Now, q could be any number. So that means it could be any natural n. Gamma could be any natural. Okay, so these two are these two n's. But now these things right here, they couldn't be anything because they're bounded in size by the size of these two things. So if q were 5, then that means this can only be up to 5 bits. Sorry, log 5. And this can be log 5 and that can be log 5. And delta, what can it be? Well, it can be log this number plus log that number plus 1, and that's each entry. And how many entries are there? Well, there's q times r of them. So that is a big number, and there's a huge number of possibilities for that, but it's a finite number of possibilities, thus it's smaller than n. And so that means that sigma 1 is definitely smaller than n by n by n, and n by n by n, it is the same size as n. So therefore, sigma 1 must be smaller than the size of n, even though it's infinitely large. Okay, so that's cool. So what next? So notice that I talked about how the natural numbers establish sort of the basic form of infinity. Z is the same size, Q is the same size. Well, what about R? Let's think about R for a little bit. So we're at 2612. So one way to think about what real numbers are is real numbers, like a real number R. You could think of them as numbers with decimals. Numbers with decimals. And the thing about numbers with decimals is it doesn't really get the big picture because there's also weird numbers like pi. Okay? So I don't want to go into too much detail about exactly what real numbers are. If you want to read about what exactly they are, you can read about what are called Cauchy sequences, which are essentially converging sequences of rationals that approximate a real number, and Dedekind cuts. And Dedekind cuts are basically the set of infinite rationals that are bigger than it and infinite rationals that are smaller than it. Those are two common ways for defining real numbers. Let's simplify real numbers, though, and we'll talk about something really, really straightforward. What we want to talk about are numbers in binary between 0 and 1. Okay, so these are numbers that are smaller than 1 that we're going to write in binary. So what do I mean exactly by that? What I mean by that is that we're going to represent, and we'll call these IBS. That is for infinite binary sequence. For example, the number 0 as an infinite binary sequence is 0 is dot 0, 0, 0, 0, 0, 0, 0, and so on. And the number that would be 1/2 would be 0.1, 0, 0, 0, 0, 0, 0, and so on. Okay? And there's some number that would be like, pi divided by 10, and that would be some bunch of digits, you know what I mean? Because we know that pi is infinite many digits, and it's like 3.14. Let's divide it by 10. Now it's 0.314, and there's some way of binary encoding that whole thing. And it takes infinitely many digits because we know that pi has infinitely many digits. Okay, so that's what I'm talking about when I talk about an infinite binary sequence. We can represent an infinite binary sequence as a function that goes from n to either 0 or 1. Okay? So now we want to ask the question, is that countable? Is IBS countable? Is it countable means that does there exist a function, f, that takes an IBS and returns an n? Or we could talk about it the opposite. We could say that is there a function that takes an n and returns an IBS such that it's 1-to-1 and it's onto. Now what would this mean? This would mean that we have these infinite binary sequences, these numbers between 0 and 1 that we write in binary, and is there some order that we can visit them? I claim that it is not the case. There is no such function. So I'm going to say that it is not true that there exists a function f that goes from n to IBS, okay, where two things are true. One, for all x and y that are inside of n, f of x equals f of y implies x equals y, and for all z inside of IBS, there exists an n inside, there exists an x inside of n such that f of x equals z. Okay, so that is not true. All right, and we know that when we're proving a negation, the way that we do that is we flip the quantifiers and we move the negation inside. So this is equivalent to saying for all f inside of n IBS, and I know how the proof works. So the proof, we're going to prove that this thing on the bottom isn't the case. So what we would get is it's not the case that we got one-to-one f and onto f. Okay, let me move that up actually. Okay, and so that is the same as saying for all f n IBS, either it's not one-to-one or it's not onto. And remember, one-to-one basically means the thing on, if it's not one-to-one, then that means that the thing on the left is bigger. And if it's not onto, that means the thing on the right is bigger. So I know that the thing on the right is bigger, so we're going to do that proof. So we're going to prove that 2614, that for all f from n to IBS, it is not the case that it's onto. Now what does that mean? That means that for all f n IBS, we do not, for all z inside of IBS, there exists an x inside of n where f of x equals z. Okay, so now we negate that, which means we flip the quantifiers. So we then get, for all f n goes to IBS, there exists a z inside of IBS where for all x inside of n, f of x does not equal z. That's the theorem that we want to prove. Okay, so that means that we are going to be given an f. So someone believes that they've come up with a function that is onto that goes from n to IBS, and they call that function f, and we're going to tell them that it's not one-to-one. So then what we need to do is we need to choose z. Well, remember, what is z? Z is a function, right? Z is a function that goes from n to 0, 1, right? And so we're going to choose the following function z. We're going to say that z of a, so a is the digit. So remember, z is a function that you say, tell me the 800th digit, and it tells you the 800th digit. Tell me the 20th digit, it tells you the 20th digit. And here's what z is going to do. What z is going to do is this is going to return the negation of f of a called on a. So it's going to look at this function f, and it's going to look at the 800th number. And then it's going to look at the 800th digit of the 800th number. And then it's going to return whatever that isn't. Then we are going to be given x. And we need to prove, must prove, that f of x does not equal z. Now, what does it mean for a function to not equal another function? Well, two functions don't equal one another if there exists The way that we prove that is that there must exist some number b inside of the naturals such that f of x of b does not equal z of b. Okay, because these f of x and z are functions, so we can't directly compare them. The way that we compare them is by looking at what happens when we call them. So then that means that we have to choose b. And we're going to choose b as being equal to, well, really we can choose anything, but let's just choose, I don't know, x. So that means that we have to show that f of x is not equal to z of x. Well, what is z of x? Well, we'll just look at it. Well, z of x is equal to the negation of f of x of x. Well, is f of x, which is either 0 or 1, is it equal to not 0, 1? No, it's not. Okay? This is the trivialist thing that we could do. So this is definitely true. Therefore, we now know that there is no onto function, and since there's no onto function, that means that n and IBS must not be the same size. All right, so why is that cool? Actually, and let me just step back one moment from this. What really goes on in this proof? What goes on is that we have all the natural numbers. Let's call them I. And so every one of those natural numbers, there's 0, 1, 2, 3, 4, 5, etc. Right? And then there's f of I, which is what happens in the function that was given to us. And it's some number, like maybe it's 0.110101, whatever. Okay? And this next one is like 101110. And this one is 0.00111111. They come in some order. I don't know what order it is. It's just some order. Okay? But nothing ever appears twice. And this one is like that. Okay, so they're in some order. What we do is we create a new number. We create a new function, z. And that new function z is a particular number, right? It's an IBS. It's a number that we're saying isn't in the table. And so what number that is it is 0 dot, we flip this one, 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 and so on. So it's that number, so it would be 0.0, and then 1, and then that one would be a 0, and then that one would be a 1, and then we need the fifth one, 1, 2, 3, 4, 5, 0, and then we need 1, 2, 3, 4, 5, 6, that would be a 1. And so this number right here, that is z. And that number ain't in this table. And it ain't in the table because it is different than every other number in at least one spot. Namely, it's different in the ith digit. The ith number is different from it in the ith spot, and that is guaranteed. Because this number is defined as being different from that one. This is called Cantor's diagonalization proof. Okay, so now what do we know? We know that sigma 1 is smaller than n. And we know that n is smaller than IBS. So, what is next? We're going to prove that IBS is the same size as all. And here's the way that we do this. Recall that all is equal to the power set of sigma star. So that means it's equal to the power set of epsilon 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, and so on. Okay? So if it's equal to that, then that means that what is the power set of that? Well, it contains the empty set, right? It contains the set that just contains epsilon, It contains the set that just contains 0. It contains the set that just contains 0, 0, 0, and so on. It contains the set that contains epsilon and 0, or epsilon and 0 and 0, 0, and so on. So it contains many, 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 many sets. All right? Here's what I claim. All is actually the same thing as IBS. And here's why. We're going to label each one of these with a digit. Sorry, with a natural. So this is going to be 0, this is going to be 1, this is going to be 2, this is going to be 3, this is going to be 4, this is going to be 5, 6, 7. Each one inside there is the lexicographic order of it. Okay? Now, the elements of all are subsets of P sigma star. Sorry, they're subsets. Sorry, let me fix this. They are subsets of sigma star. So that means that each one of these, basically what it does is it's an assignment of each one of these numbers to either 0 or 1, whether it's in it or not. So for instance, empty says 0 to everything. So that means it's a function that takes in x and returns 0. So essentially what we're saying is that if f is inside of all, then f of I is equal to whether or not the lexicographically ordered thing inside of I is inside of A. Is that the right way to say this? Yeah. Really what we're doing is we're saying that we can make a bijection between all and IBS where we take in, yeah, that's the right way to say this. Okay, that f is a function that takes an all and returns an IBS. And f of a is a function, so that means it takes a number, and what it does is it's going to return whether or not the lexicographic ordered string is inside of a. And this right here is one-to-one and onto. It's one-to-one because nothing is left out, because every one of these sets is represented by here, and it's onto because every sequence of bits corresponds to some set. So what that means is that since sigma 1 is the same size as n, and n is definitely smaller than IBS, but IBS is the same size as all, therefore sigma 1 is smaller than all. And if sigma 1 is smaller than all, then that means that there are an infinite number of things that are not possible to program. Because remember, sigma 1 is all the things that we could even conceivably write down a program for. And that is infinitely smaller than all of the possible strings. Exhausting, I know, but now we know that there are not just one thing that we can't do, not ATM, but there's an infinite number of things that we can't do. So depressing. We'll finish up the class next time. Later.